Okay, all right. We good? Sounds good? Recording? All right, good to go. So thanks everybody for coming. Nice early on Saturday. I know it's a tough time. I didn't even want to be here, so no, I'm really happy to be here. So my name's Ben. This is kind of a follow-up talk to a DEFCON talk I gave at DEFCON 24. And I just wanted to kind of start off by saying I really, really love Derbycon. It's my favorite con. It was my first con ever, and it was the first con I ever spoke at as well. I gave this talk called A Bug or Malware, and I was really obsessed with this kind of overlap between bugs and malware, kind of the exploit vulnerability synergy. And I had this idea at the time. I thought I'll write a spell checker and I'll invert all the logic. And we'll call it a spell wrecker. So it's something that creates, realistic typos. And so I wrote this, and I demoed it. So I have a little thing here that's kind of showing it turns red when it creates a typo. And the idea is the faster you type, the more typos it creates. And then as you slow down, it starts to behave and creates less typos. And I thought, I had seen this talk at DEFCON years back on YouTube that would corrupt the runtimes of managed code languages. And I thought, I'll just embed this in the Java virtual machine. It'll be really cool. I'll have this awesome demo. And I couldn't figure out how to do it. It was just too hard. So I just proposed this as an interesting problem. How do we detect the difference between the two? And then that kind of, spawned an idea in me. I thought, this shouldn't be that hard. So I'm going to make a tool that makes it easy to do this type of attack. So that's what I presented at DEFCON, was kind of the first release of that tool, kind of generally how it works. And now it's fun to kind of bring this full circle, and I'm bringing it back to Derbycon. So what's the talk today? It's really just a bunch of demos, a bunch of stuff I kept working on, make things a little easier, a little better. And we're going to kind of go through that today. So first of all, let's just kind of get everybody on the same page. We'll have a little recap. So I'm talking about evil Java. What are we talking about? So let's look at the first demo here. Okay, so we have our standard Windows 7 machine here. I'm going to open up a decompiler. JDGUI is a nice free decompiler. And I'm going to decompile this little Hello World program. Nothing up my sleeves here. It's just a standard Hello World program. So if we run it, what would we expect to see as the output, right? Just standard Hello World. But that's not the case for this machine. So here I'm going to go ahead and run it. Just pass in Hello World here, and it prints off Hello World backwards. So, what's going on here? So let's dig a little bit deeper. All right, so we kind of have to understand, what is a managed code language and how does it work? I'm studying Java at the time, so let's look at how Java works. So Java, we have our source files, our .java files. We shove those all into a compiler, and it spits out these .class files, which are bytecode. And then you can just zip them all up and rename .zip to .jar, because Java's fancy and we have jar files, and a jar file is just a zip file. But what's cool is we can take that jar file and somehow run it on all these different operating systems. It's Windows, Mac, Linux, Android, all these different operating systems. They somehow all work, right? We don't have to create a different jar for each target. And so how does that work, right? Well, they have this virtual machine, which is kind of in between, interpreting the Java bytecode instructions and then running them with the corresponding commands on the target machine. So let's dig a little bit deeper in there, right? We had our Hello World jar. That's just a standard thing. We didn't change anything there. So we must have changed something below, this point onward. And so if we dig a little bit deeper, we see, well, the Java virtual machine also comes with a lot of standard libraries, right? All your networking, all your file I/O, everything there. That's kind of comes with Java. And those are all developed in the runtime libraries, which are specific for that operating system. So the idea is, let's corrupt those, and then we can affect all of the programs which are running on the virtual machine. And that's really, kind of the idea behind managed code rootkits. And, this is not really a new idea. It's been around for a long time. You manipulate the standard runtime and, standard libraries, and it affects all of the applications that are using that library. It had been done back in 2010 on Java, C#, but actually I've seen a lot of interest in doing this for Python recently. There's been a few talks. There's one at ThoughtCon. I saw some at B-Sides of people kind of messing around with the Python precompiled libraries. There's a few advantages to doing this. It's kind of out of sight, out of mind. So if you have someone auditing a system that's been, exploited, maybe they're not going to audit the full Java runtime libraries. That's just kind of a lot of work, right? And we kind of assume they're good. So we might be, overlooked if people don't know about this potential vector. And it's also nice because if we're going to make a rootkit, we're going to put something in the runtime libraries. We're developing with a fully featured language, right? It's object-oriented programming. If we do the attack right, it's portable. It's platform independent because we're doing it on top of the virtual machine. The idea was, let's just make this easy. It's not that hard to do conceptually, but it's a little tedious, right? And if we can kind of lower the barrier to entry to make this easy for everyone to develop these, then we'll become more aware of this attack. Since it had been around for, since 2010, people weren't really talking about it. I thought, let's make something to make people talk about this again. So, how are we going to modify these runtime libraries? Well, we could just open it in a hex editor, and this totally works. My first kind of proof of concept was, I'm going to build the spell checker, and I'll just intercept the key event and replace it with the letter X, and see if it works. So that's easy because I haven't changed like parameters. I don't have to recompute things in the stack frame. But it's a pain because imagine you change like a variable, and then you have to go find all the references to that variable and change how those references access that variable as well. So there's this kind of butterfly effect with all the changes you make. So doing that in a hex editor would just be no fun at all. Well, the next idea is, something that most people will do is they'll use some intermediate representation. So something like Smalley for Android, they'll, back Smalley and Smalley, they'll kind of decompile an application to this intermediate representation, edit the intermediate representation, and then recompile the application and throw it up there with their backdoor or whatever in there. That's fine. That totally works. In fact, that's, the first approach I took to this tool, and then I realized we can do a lot better. Because it's still tricky. Developers don't write code in these intermediate representations. So it's kind of hard that you don't want to learn a whole new language. We already know a language, let's just stick to that. So the other approach is, we just decompile whatever it is we want, and then hope that the decompiler didn't produce a bunch of errors or that it actually decompiled it correctly, which is, kind of a pie in the sky idea. That's just not feasible most of the time. That only works for very small, like toy examples. So this is ideal, but it's just really not going to work in the general purpose. So we want to kind of get to that source level, and this was kind of the idea I came up with. So, it's easy to write source in general. That's how we develop programs, and it's easy to convert that source into bytecode, right? We just shove it into a compiler. That's what the compiler does, and then, I read a paper that kind of put it all together for me. It's easy to inject, replace, and merge whole methods at a time inside another compiled class file. And so this is a library called ASM, and it lets you do some bytecode manipulations. And it's really a very popular library. It's included in almost all these as a front end to all these other tools, so Smalley and all those sort of things. And then we have to realize that, what's in a class file, what's in the compiled bytecode. It's just declarations of fields and methods, and those methods have the body with all of the code. Now, all of that code, the assignments to those fields, the reads to those fields, everything that happens in the program is actually declared somewhere within a method body. So if we have this ability to add or replace or manipulate some method body or whole method at a time, we can really cover all of these use cases just by writing source code. And the trade-off is if we want to edit one little line inside a method, well, we just have to rewrite that method. So that's kind of the trade-off, and I said, let's go forward with that in mind. So kind of conceptually at a high level, let's just look at what's happening. So we have this new source that we've developed, and we have, maybe this source in the runtime. Maybe we don't actually have some proprietary code. Maybe it's not OpenJDK, it's some implementation of a JVM that we don't have. So let's say we don't have the source code. And, there's the file class, and we want to change the file class. Maybe add this new method foo to the file class, right? So we can, write a new version of foo, just write a class which extends, file, and then, implement that method. And all we have to do is copy that whole method into the other target class, right? So that adding code's pretty easy. If we can add code, it's pretty easy to replace code. We just find the one that collides and replace it, right? So replacing code's easy. Deleting code is easy, right? So we can find the one that collides with the method we want to delete, and then just remove it from the resulting class. But what if we want to kind of hook a method? Well, this one takes a little bit more work, and this is usually what we want to do. So if we have a method, say exists, and we want to change the way the exists method works. And maybe we want to change it the way it works in some cases. So let's first rename and kind of hide the old implementation from everybody else, and then take the new one that we want everybody else to see and add that, right? So in this version, we have a method called exists, which will do something and then eventually call this old version of exists, which is only accessible to this method. Okay, so that's kind of the basic idea. And if you notice, in each of these versions, we kind of just have to say what type of operation we want to do. So in this case, it's delete this method, or it's merge this method, right? And this is really what the tool is doing underneath. So I created this tool called JReFrameworker. There was a previous tool called JReFrameworker, and I just kind of liked the name. So I thought, I'll just steal the name, but we'll make it different. It's a Java project, so normal convention for a Java project is we just slap the letter J in front of it. And so I did that, and I thought, cool. And then I noticed, oh, it spells JRE in front. So I thought, yeah, okay, that's cool things. That's definitely the name. And then I got up to DEFCON, and I realized, I don't know how I want to pronounce this. Is it JReFrameworker, or, yeah, I don't know. So I don't have a good way to pronounce it. That was, if you're going to name a project, maybe think about how to say it out loud. That's just my advice. But, so I created this. It's an Eclipse plugin. It does all the implementation for you in the background. You don't have to know anything about bytecode. It's free, open source under the MIT license. You guys can do whatever you want with it. And we kind of develop these modules of how we want to manipulate whatever the target is. So we'll go through that. Right before DEFCON, there was a fun tweet that I found. It was, just what the internet is in dire need of, a well-engineered malware development toolset. And I thought, oh, that's kind of a compliment. He said it's well-engineered, so cool, I'll put that in my talk. And I never really met this guy, but just some guy on Twitter, right? All right, so how do we mark those methods in the source that we want to overwrite in the library? There's something called an annotation in source code. So a Java annotation, just the definition for Wikipedia is it's just syntactic metadata that we're going to add to the source code. And there's three types of annotations. So one is something that we add to the source code. It never ends up in the compiled binary. It's just kind of extra information in the source code level. There's code only, which is something that will end up in the bytecode, but it's completely ignored by the virtual machine, the Java virtual machine. It doesn't influence anything at the runtime of the program. And then there's ones where we can actually, add some information so that you could use reflection and query something about the program. A lot of libraries will do this. So you'll say at entry point, and that's the entry point for some web handler or something like that. So you can kind of say any method is the handler for this response. But we can use this code only when we don't really want to, add anything to the resulting runtime. But we do need to kind of mark what we want in the resulting bytecode. And so I thought, the idea is we'll just temporarily mark these parts using these annotations, and then we'll feed it into some engine which is going to know what to copy and replace or merge or delete, whatever operation it is. And so we kind of end up with this basic set of annotations, right? So we have the whole class level, the type, the method, which is the function, and then the field, the global variables. So we can say define a new type, or if that type exists, go ahead and replace it. Same thing with methods and fields. Or we can merge types, so we can say, I want parts of this class to end up in this class, or I can say I want this method to end up in this method, but preserve the original behavior, because I may need it. Okay, so the second demo, I'm going to do this one live just to show you everything works. Everything else is recorded just to save some time. So this one we're going to do, I want to make a secret hidden file. So we'll have the virtual machine lie whether or not a file exists for certain types of files. Okay. So you've got your Eclipse set up. Once you've installed the plugin, it's really easy to install. We're just going to create a new JReFrameworker project. And I'm going to just say this is a hidden file. And okay, delete the log here. Okay, so first let's just make some test code. How do we test and know if our manipulations are working? So I'm just going to create a file called test, give it a main method, and what do we want to do? Well, let's create a file. Let's give it a name, which is secret file. Come on, Eclipse. Okay, all right. Then let's write to that file. So I'm going to create a file writer and pass in that file. Oops. I guess I can make this bigger so you guys can actually see it. Huh? Okay. All right. Could throw an exception. That's fine. I don't really care. Let's just write something to the file so that we know it exists. So I'm just going to write blah. And then we'll close the file, flush it all out. Now let's print true or false whether or not that file exists, right? We know the file exists, we just wrote to it, right? So let's see, file exists. So there's a method called exists, turns true or false whether or not a file exists. And then let's just do a little cleanup for our test code. Let's just delete the file when we're done, right? All right, so let's just run this. We haven't, changed anything yet. We're just writing test code. So file exists, true, yes, right? We're happy. So now let's create a new class, which is going to be the logic we want to merge into the runtime. So I'm just going to call this hidden file. We can call it whatever we want. I'm just going to put in another package. All right, so I want to reuse some of the behavior from the runtime, and this is going to be how we declare what target we want to merge it into. So we extend the object that we want to merge this logic into. So the file class here. And everything in Java is an object, so we can always extend an object. There are cases where we can't extend an object, and I'll talk about that later. All right, so Eclipse is being really helpful here. It says, you have to declare this constructor, so that's fine. I just want this to compile, so I'll just add the constructor, no big deal. Now let's override the exists method. So I'm going to say exists, and let's just say return false. Actually, let's prototype out all the behavior. So I just want it to return false regardless if the file exists, if it is that secret file, right? So if let's say if it's a file, because this could also be a directory, but if it's a file and the file name is sorry, make this bigger again. And the file name is that secret file, then let's just lie and say, nope, doesn't exist, regardless. Otherwise, let's do what you would have normally done, which is our parent implementation in the file. So that's super.exists, right? So just behave like you normally would if it's not a secret file or it's a directory. Okay, now let's make sure this is a source level annotation. So let's make sure that I actually overrode the right method. So this method actually exists in our parent. The override annotation is just a sanity check. It doesn't really do anything, so I can get rid of that. Now, if I wanted to test the behavior, I could test it right now. I still haven't changed anything in the runtime. But what I could do is, let's use the hidden file definition, and let's go ahead and run it and just see, that everything is working fine. Okay, so it says the file exists, false, good. Now, I want to actually say we should merge this into the runtime. So I'm going to say I want to take some types of this class and put it in this class. So that's a merge type. And I don't really care about this constructor, but I do care about the exist method. So I'm going to say I want to merge this method into the runtime. Okay. Now, there's one thing I have to do. I have to say which target I'm actually interested in. So I'm going to update this XML file to say the target libraries that I want to manipulate. So I'm going to add a new target, which is name equals, this is the runtime.jar. And there is a difference between runtimes sometimes on the class path. So I'm going to say, yes, this is a runtime. Save that. Okay, so now we can see our builder is working in the background. It has built out a new, well, almost finished, building out a new version of our runtime library for us and sticks it in the build folder here. So now if I run our test class, let's change it back to the original file. Okay. So if I run this guy with the standard version of Java, right, it should say, yes, the file exists. But with our manipulated version of the runtime, it's going to say, no, it doesn't. Right? So in this case, we're actually using the file. So this is just a way to test it locally without having to actually mess up your runtime. So the first time I ran this, I didn't have that, and I messed up my Java quite a few times, actually. So I've added quite a few safeties so that you don't mess up your own version. All right, so now we have one more thing. So we've developed this locally, but we wanted to do this to our victim, right? So what we can do is we can export part of this logic, right? We just need to know what are these manipulations that we're going to make on the victim, and we can export a version of the engine that will make just those manipulations to our target. So this is our payload dropper. So we can export that guy. I'm just going to stick him on the desktop here. Sure. And then if we run this on our victim, it's going to make those same changes. Right? And that's actually our next demo, so we might as well do that right away. So I recorded that one just to make it easy. Right? So we export our payload dropper. And then we come on over here to our version of Kali and load up Metasploit. Right? Now this is post-exploitation, so you already have to have a shell on your victim. Right? And most of the JREs are installed somewhere with administrator privileges, so you're going to need to have a system on the victim machine. So that's just something you need to know. All right. So we're just testing, everything behaves as normally. The file exists on the victim. We just uploaded our test script just to know if it works or not. Now, let's go ahead and let's see, what are we doing here? Okay, yep, we load up our custom JReFrameworker module. This is a post module. It's on the GitHub, everything's open source. And we've specified that dropper as our payload that we want to use. And the session, we have one session already. So I'm just using the PSExec module here for testing. Now we go ahead and run this. So it's going to execute the jar on the victim machine, and manipulate the runtimes and replace them for you. So now if we come back over here to the victim machine, and we run it again, it doesn't exist anymore, right? So we can remotely make these changes on our victim, and each victim is going to have a different version of the runtimes, which are all a little bit different, but that's okay because the bytecode manipulations are computed on the fly, so we can do this generically, develop one exploit module for all of our victims usually. Okay, so let's go back to the slides here. Okay, so the rest of this talk is just kind of the new shiny. So what have we been doing? I've kind of changed over the workflow quite a lot. A new exploitation kind of persistence stuff was kind of what I was digging into. So tons of bug fixes. I had to deal with things like if a jar is signed, you need to know how to unsign it and re-sign it with your own key. Now, the Java runtime libraries actually aren't signed at all, so you don't even have to deal with that. And actually, it kind of makes sense because what are they going to check the key with, right? I'm already root on the system. I'm just going to disable that check. So at this point, it's already game over for them. So annotations, we added quite a few new annotations to kind of handle some edge cases and you know, what happens if you can't extend a class? What if it's marked final or it's hidden, something like that. The modules used to be all kind of like hard-coded paths. Everything's symbolic now, so you can export a module. It works on different versions of Eclipse. General workflow issues. I actually added unit testing so I can find all the bugs that I've been introducing. And lots of improvements to the dropper. The dropper used to just be a main method, and I learned this the hard way when I exported the dropper, went to click it and drag it over to my virtual machine, but accidentally double-clicked it and changed my my runtime on my host machine. So I added a safety, right? So now if you want to run it, you have to pass a safety off flag just to make sure you actually want to execute this payload. And it was a sneaky payload, so it took me a little while to find it. Then there's lots of other things. So we can do things like, well, you know, what if the I don't want to manipulate it right away? What if I want to manipulate this runtime later? And so we can kind of watch things. We can make sure we're single instances. We can watermark things so we don't actually manipulate it twice. You can print all the payloads, lots of stuff like that. So in the next demo, this was something I was interested in, is so you've manipulated your victim's runtime, but then a new version of Java comes out. So what they're going to do, they're going to run the updater and blow away all your changes and install a fresh version of Java, right? So that's kind of a pain because you lose your persistence or whatever your manipulation was. So I thought, you know, we can deal with this. We've already specified a way to generically, you know, manipulate the runtime. So how do we do that? So I'm going to come back over here. So the Java update client. Oh, and then I guess you can also, if you want, you can bundle up this jar into an exe. You can encrypt the payloads. There's lots of tools to do that. Okay. So what I'm going to do, so we've already got root on our system. What I'm going to do is grab a copy of the Java update client and pull that down. And then we can use Metasploit to generate a shell command to run the our shellcode to generate to run the dropper to manipulate the changes again. And we can take Backdoor Factory and backdoor the update client so that when it runs, it waits until you install the new version of Java and then runs your bytecode manipulations again right after you've updated it. So now you have a brand new version of Java with all the new features, and then you can add your backdoor into it. So you get to upgrade your exploit later, which is kind of fun. So let's see. Okay, so I went ahead and uploaded the backdoored version of the update client. Just restarted here to show, you know, we've lost our session. You know, it's okay. We'll take care of this in the future. So we go ahead and run the update client. We install this. Java says, hey, you know, we've got 3 billion devices, which is kind of fun. You know, most of that is actually for SIM cards, because SIM cards actually run tiny little Java programs, which is something I'd like to dig into in the future. But anyway, we run our update client, and we notice this guy up here popped up. So I didn't hide the background process just to show you what's going on. So it's just sitting here waiting for the new runtime to appear, right? And as we run this guy, it says, "Hey, I found a new runtime that I didn't know about before the updater ran." And it says, "Let me just fix that for you," right? So now we've got a new, or sorry, I had to restart the machine because of the system variables changing. But we've got a brand new version of Java. We were on Java 8.0 originally, and now we're on Java 8.0 144 update. We run our test hidden file, and it still says there's a hidden file. So we're happy about that. We can survive Java updates. The latest version of the Java update client actually has some stack guards in it, so it makes it tough to do it with Backdoor Factory. You have to actually do it by hand. So I haven't figured that one out yet, but that was only added recently, so you can still play around with this. All right. So we can survive our Java updates, so that's cool. Now let's go back to, you know, what are some of the improvements to the annotation. So I thought, you know, originally I didn't think it was very interesting to remove functionality. But this is actually kind of useful. Maybe there's a deprecated method and you really don't want people to use it. You can just rip it out of the runtime. No big deal, right? So we added a purge version of all the annotations, so we can purge a type, method, a field. Then there's a lot of classes. In fact, most of the interesting classes that you might want to manipulate are already marked final because the Java runtime developers have said, people really shouldn't be extending this class and changing the behavior. So that's kind of nice because now I can just say, what are all the final classes? These are all the interesting ones I want to mess with. And we have an annotation which says, basically mark this not final. So now I can go ahead and manipulate it. We can do the same thing with the visibility, so the public, private, protected, that sort of stuff. Change those, and now we have a new version of the runtime that we can extend and work on like normal. Once you have this, you kind of have to do things in steps. So you might first have to mark a class as not final, then you can extend it, it compiles again. So you have to be able to define different phases. In the first phase, I want to do these manipulations. Second phase, I want to do this. So I added a attribute. So for each annotation, you can define what phase that will execute in. So you can have kind of multi-pass compiling. Okay, so then once you have that, once you have multi-pass compiling, it's really nice to basically not have to worry about this and let the Java or the manipulation engine in the Eclipse builder do this for you. So previously you just have to clean a project or rebuild it from scratch each time, and now you can just say, basically every time you save a source file, it's going to compile, detect that, whether you added, modified, or deleted a source file, it's going to detect what are the changes I have to make in order to recompile this from the last change set. So that is the next demo. And before I do that next demo, I just want to give a little background. Oh, I'm stuck. That's weird. Okay. Okay, I'm gonna. Okay, I got my mouse back. Okay, so let's run this guy. Okay, so what are all the? Okay, here's the background. So my first Derbycon talk, I was kind of interested in this bug and malware area, this intersection between the two. So I just took an old Java CVE as a Java web applet, kind of drive-by browser attack. And it was 2 years old at the time, and I just started kind of simply doing some simple refactoring, uploaded it to VirusTotal, see how many AV detected it, right? And you can just do things like change the name of strings, obfuscate a few things, and add some reflection, and like almost nobody detects it. Do a little XOR packer, it's nobody detects it. And then at DEFCON, I thought, I'll just do this again. I just repeated the experiment, same exact payloads, right? Just had the things reanalyze it. And, we got a little better, but not much better. It's just kind of fun to pick on AV sometimes. But after DEFCON, like 2 weeks after DEFCON, one of the AV is actually detecting it. So good job for them. But actually, they're just keying off of what I did in the XOR packer, so you can just change that. But what is my point here, right? So it's easy to get past AV, maybe, right? But is anybody detecting the counterpart to that? Nobody's detecting the vulnerability, right? So what if I do something like a reverse bug patch? So what if I unfix a bug? So this bug was fixed in Java 7, update 7. There's a nice Metasploit module for it, but it doesn't work, because everybody's running almost Java 8 now, or at least an updated version of Java 7. So I thought, let's just unfix it, right? So what did they do to fix it? Well, they deleted a few classes, so I'll just shove them back in, right? And they basically deprecated a method, so you can't use it anymore. So I undeprecate it, I add it back. And of course, you upload the vulnerability, nobody's going to detect that. Why? We're not even looking for that, right? So let's use that. This takes a couple phases. So this was a good demo of the incremental builder here. All right, so go ahead and run this. I'll just kind of zip through this to save on time here. But we want to manipulate the runtime jar, so we set that. This is the original kind of proof of concept exploit. If we run it, in the modern version of Java, we just get this stack trace because the field and the class, they don't even exist anymore, right? So no big deal. But if this exploit's successful, we should pop up a calculator. And that would mean that this applet was able to bypass the security restrictions and escape its little sandbox environment. So we have a couple things. All these classes are marked final and private, so you can't access them. No big deal. Let's just make them not final and public, right? So we can extend them like normal. Now we have a couple classes we have to drop in. We need this kind of like little privileged action. So it's an inner class, so I kind of break it out into multiple steps. Then I drop in the get field, which was a kind of a method that was removed because it wasn't really needed. Now we have this class where they had deleted the class finder, or deleted a few methods out of the class finder class in the Java bean, and they deleted a few methods out of the method finder class, so let's just add those back in. Let this build off on the side, it's just building all the things, and then if we run it, whoops, too quick. So we go ahead and run it in the manipulated environment, and we can pop a shell, or not a shell, but a calculator, right? So now our original exploits that are built into Metasploit work again. So that's kind of fun. So I fast forward here. So we've got our Windows 7 victim, and I forced the Java console to pop up so we can see when we ran the our Metasploit module here that's running the web server with our exploit code on it, and we get our victim to go to that, and they run that jar. They're going to get that same stack trace that we saw earlier. But now we go ahead, manipulate the background, the runtime, and we've added basically a backdoor for ourselves to come back to later. And now if they go to this, it's going to pop up. It's actually going to upload Meterpreter. We get our shell. We have another session, so we now have 2 sessions. So I thought that was kind of fun. And I had actually done this demo or made this demo for DEFCON without the incremental builder. I kind of did it the hard way. And then I realized there's like a ton of people here. I got nervous, and this demo that I spent a month on, I completely forgot to give it and ended my demo 10 minutes early. So anyway, so you guys get to see it now finally. So okay, so could we just do some automatic backdooring of the Java applications? Sure, we have all that ability now, right? So the idea is basically find the main method, spawn a new thread, execute your Meterpreter Java payload. No big deal, right? So that's pretty easy. We just grab the source from Rapid7. They have the payload for the Meterpreter shell in Java. This is basically the equivalent of running your Metasploit framework Venom command with your IP address and port to connect back to, generating your malicious jar. And then all we have to do is extend the class that we want to replace the main method for, start a new thread, run our payload in the background, and then call whatever the main entry point was, right? So the only thing that's really changing here is we have this, what class do we want to change? And in Java, when you have a jar, you always have to specify that main class, so we can easily write a script to do this. So I have a demo that does that. So I took the Java decompiler, and we'll just backdoor it real quick. Make this big. Right? Okay, so we drop in all our class, the incremental builder runs, manipulates all these files. We spit out a modified version of the jar. And if we run it, I added a few printouts just so we can see what's happening. Basically, it fires off the Metasploit payload, and then the standard main method runs and opens the decompiler, right? So the user doesn't really see what happens in the background. There does seem to be a bug in the reverse TCP shell Java payload right now that isn't fixed. So I was running into that error, so I didn't show the stager connecting back, but I'm pretty sure that all works just fine once they fix that bug, or if you go back to an older version. Okay, so I thought, that's a cool demo. Everybody likes to see the backdoors and the shells pop up, but it's really not that interesting, right? What we want to do is manipulate things in interesting ways. So what we can do is integrate this with something like a program analysis tool suite and a source code generator that's going to write the source code for what you want to manipulate, right? So Java Poet's a cool source code generation library. Atlas is a tool that I use a lot. It's similar to like IDA Pro, but for Java bytecode, Java source, C source. And we can come up with some interesting scenarios. So in this case, what I wanted to do was basically add a check to make JDGUI prevent itself from decompiling itself, right? I like these kind of recursive things sometimes. So let's look at that demo. So this is actually interesting because we have to kind of find, well, where would that check happen? And you can kind of go through a process of thinking, well, how would I build that, right? Maybe I could just take the file hash of the program, change the program. Oh, I've changed the file hash, right? So it has to be something not a file hash, right? You could look at kind of parts of the program, or we could be a little smarter and we could say, we could let it decompile normal programs, but only look and see if it's decompiling itself, then it should change, right? Then it should block you, right? All right, so I'm just running JD GUI on itself here. This is what's inside. It's not that interesting. Actually, it's pretty interesting. There's a lot of interesting code in there. And the source code for JD GUI is actually not available. There's just a snarky comment that says, well, you have a decompiler, don't you? Right? All right, so this is basically I've generated some intermediate code and then used the program analysis tool to map out all the relationships in the program here. And I've added kind of a programmatic, this is a little Scala interpreter. I've added some wrappers around all the operations to create projects, to generate source code. And the way we generate source code is by clicking on these kind of interactive graphs. So this is a call graph. I started from the main method. I started exploring forward. There's a couple approaches you could take to this. One thing I thought was, let's just find how this application uses all the file APIs, right? So we can kind of say, show me all the ways that the application uses file APIs. It creates this kind of nice abstraction around files, which makes it tough to track. So I thought, that's easier. Let's just figure out where does it call the main decompile routine. And I just guessed, right? Let's just say there's probably a routine that's called decompile. So let's just show me all the decompile routines. Well, there's 3. Turns out there's one which is kind of a wrapper in the UI interface, and then there's one which is an interface, and one that's in the kind of core decompile routine. Right? So I'm just kind of using these kind of interactive views to kind of find the place that I'm interested in. Now I find the decompile routine, and it right away has this model of a class file. You can kind of see over here. So there's this model of a class file after you've parsed the file. And it has the package names and everything, the class names. So I thought, oh, that's easy. Let's just override one of those so that if it ever sees a class name, which is the package that's unique to this application, it just throws up like a prompt and says, no way, you can't do that. Right? So the way that we do that is we just click on the node that or the method here that we want to manipulate, and say, in this command line down here, I want to merge this method of what I've selected. It generates the source code up here for us. And we get to, it kind of skeleton stubs it out for you, so then you just get to replace what it is that you want to do. So we have to add a main method, or a constructor here. And then so in this case, what I want to do is, I want it to behave like normal. So let's call the parent implementation, get the result. And then if the result is, has a package name, which is JD and core, which is the part of the core decompile routine, then let's just pop up a message that says like no, and then just quit the application, right? So if we run this guy, everything works like normal. But then once we try to access any of the classes in the main decompile routine in this JD core folder, it just pops up a thing and says, I'm sorry, but your authority is not recognized in Fort Kickass. Right? Okay. So let's go back. We're getting close to the end here. But something that I was interested in is this idea of context-aware malware, right? So let's just flip the question. In this case, we manipulated the decompiler application itself. But what if we want to manipulate the runtime so that the runtime says, no, you can't use files if you happen to be an application that is a decompiler, right? So we can make it so that decompilers can't decompile their runtime, right? So we can kind of add some anti-RE stuff to this. All right, so how do we do that? Java has a lot of reflective features to let you kind of do this meta-analysis at runtime. Actually, I want to spin back. So at the DEFCON talk, I was really interested in this idea of just interesting triggers, right? So I had this little program here, which is called a Tim Burton object. And if you call a method called Beetlejuice 3 times in a row, anytime in your program, it's going to do something interesting because the runtime's looking to see what is the name of the method that's calling the objects in this guy here. So I'm going to go ahead and run it. This is kind of the back end here. It runs something called main.main here, right? And this was also a demo just to kind of show how crazy you can get. And it turns out that people have actually ported all of Doom to native Java code. So I thought, let's just shove all of Doom into the runtime. And if you run Beetlejuice 3 times, it's just going to launch Doom, right? And you can go ahead and play it. It's full game. You know. And then when you quit Doom, it just starts running your normal program wherever you left off. Okay, so we have these interesting triggers. We can kind of do this context awareness in our edits. So let's override the file class that anytime something tries to access the actual path of that file, it's just going to throw an exception that says deal with it if it's from a package that has JD in core, right? So a decompiler is not allowed to access any files, which is basically just going to brick your decompiler. But your decompiler, all your other applications will work fine. So if we go ahead and run this, we run this on our victim machine. So here I'm just replacing things manually as another way to show how to do this. But you see, JD GUI opens just fine. There's a deal with it message. We try to load in another runtime, and it basically just bricks it and crashes it, right? But all of the rest of our runtime and Java applications work just fine. So that's kind of fun. Okay, so then I kind of imagine this kitchen sink demo, and just to bring it full circle, I thought, let's take our spell wrecker application. Now we can finally embed it, right? So we can have this contrived scenario where some Java developer is using Eclipse and it's acting weird. In fact, this was the change that I accidentally did. I was developing this trying to see if it works, so I thought I'll just replace all letters with the letter X. I ran my program, and seemed to work fine. I went back to Eclipse to develop my program, and I started typing, and all it would type is the letter X over and over again. And I realized, well, there's actually a 32-bit and a 64-bit version of the Java runtime, and I manipulated the wrong one. So there's sometimes you need to know where they're all at. But we can imagine this Java developer. Eclipse is acting weird. It's making all these weird typos. All the images are pixelated. So a little demo of that. So these are some of the old modules that DEFCON, I basically was just interested in trolling projects. So we go ahead and run this. If you okay, yeah. So this is kind of simulated typing because you need to see where the spelling errors were. So if we run it in the manipulated version, it makes a bunch of typos. You can kind of see down there. And then images we can run. This is a normal image. And then this is an image in our manipulated version, right? So we can pixelate things just for fun, and just kind of give people a headache and wonder why is everything weird, right? So back to this scenario where everything's weird, so we suspect so we heard these attacks, and decompiler time crashes. So we think, there's a compiler and the compiler doesn't know, right? And we update our Java and we're just saying a whole new programming language and Java forever. And I don't think so. Because studying, the JVM, the code isn't just supported Java anymore. There's a lot of languages that Java virtually